And so let's plot this for different values of R and K. And this is figure 13.4. And if I plot the thermal efficiency versus R, and so I'll do it for K is equal to 1.4, K is equal to 1.3. Now why the different Ks? And so what happened is K changes as the temperature goes up, and we saw that in the Otto cycle we're going to have very high temperatures when I do this. The value of K goes down. So if I want a better model, I'll use, this is called the hot air standard, where I'm using a value of K reflecting temperatures of around 1,000, 1,500 degrees Kelvin. And the actual engine, so why does this matter? So I have my actual engine. And so what we see is that the actual engine performance might be half of what the ideal one is, but the shape of the curve, as it varies with compression ratio, so as R goes up, we see that it's parallel. So if I can look at factors that affect the performance here, it should translate to the actual. And that's why using the air standard model works out to be pretty well in terms of doing that. So what I'd like to look at next is example 13.1, which is the Otto cycle. And just to, so you should look at example 13.1. And so we have T1 is 300 degrees K, P1 is 100 kPa, Qn is equal to 1840 kilojoules per kilogram, and R is equal to 8. And so what I did, just so because later on we might switch to English units for some problems, this relates to 77 degrees Fahrenheit, 14.7 psia, 790 BTUs per pound mass. So we see what the order of magnitude is. So if I switched over, this is a little bit less than half of what that is, just in terms of numbers and changing things. So now we're going to work our way through the cycle. So part of what this problem does is have you go through the cycle, find the various state points, etc. And so let's do that. And then we'll do some modifications to this to have it, see how I would model actual engines with that. So I always draw the PV diagram so I can pay attention to what's happening. 1, 2, 3, 4. So anyway, I have that in mind, what's happening there. And the process from 1 to 2, PV to the K is a constant. So I have T2 is equal to T1 times V1 over V2 to the K minus 1. And this is R. So T2 is equal to T1 300 times 8 to the 0.4. K for air, 1.4 from table A1. So I get 689.2 degrees K. Now I can find the pressure. I'm going to use the isentropic relationship to find the pressure. So P2 is equal to P1 times V1 over V2 to the K is equal to 100 times 8 to the 1.4. And so P2 is equal to 1838 kPa. And the process from 2 to 3 is heat in at constant volume. So process 2 to 3, Qn at V equals C. or large Qing at total volume. And so I know that Qn for V equals C is equal to U3 minus U2 is equal to C sub B T3 minus T2. And in this case, I know Qn. So Qn is 1840 is equal to C sub B 0.7176 times T3 minus T2 is 689.2. And I can solve for T3, and T3 is equal to 3253.5 degrees Kelvin. The 0.5 really doesn't matter, but be that as it may. For V equals C, and I always look at PV equals RT. So for V is a constant, T over P is a constant. So I have that P3 is equal to P2 times T3 over T2 is 1838. Times 3253.5 divided by 689.2. One really doesn't need the final decimal points, but this way you can follow it. So then P3 is 8676 kPa. And now we need to go the process from 3 to 4. Again, it's PV to the K, it's isentropic. So T4 is equal to T3 times V3 over V4 to the K minus 1. If we look, we see that V4 is the same as V1, and V3 is the same as V2. So this is 1 over R. So this is equal to 3253.5 times 1 over 8 to the 0.4. So T4 is equal to 1416.2 degrees K. And P4, I again use the isentropic relationships. P4 is equal to P3 times V3 over V4 to the K is 8676 times 1 over 8 to 1.4. So I have P4 is equal to 472.1 kPa. So now we've gone all the way around the cycle and found various states. So now we can find, we know the heat in, we can find the heat out, we can find the network, all that sort of stuff. And so we'll go through that now. But we have these values. So the purpose of this example was to look at how you go through a cycle. And now we'll complete this. So the thermal efficiency, 1 minus 1 over R to the K minus 1, 1 minus 1 over 8 to the 0.4, or the thermal efficiency is 0.563. Q out is equal to U1 minus U4 is equal to C sub B T1 minus T4 is equal to 0.7176 times T1 300 minus T4 1416.2 and we get the Q out is equal to minus 801 kilojoules per kilogram. And so I have what that is. I can do W net is equal to some Q. And so that's equal to 1840 minus 801 is equal to 1039 kilojoules per kilogram. And if I did the thermal efficiency as W net over Q in, so if I went through this, the thermal efficiency W net over Q in, if I do that calculation, I get 0.564. So it's effectively the same number. The difference here is round off simply because I rounded off different values of temperature and not carrying out the 20 different significant figures. And let's find some more characteristics that we want to do with engines. So one of the things that we look at is mean effective pressure. And we've done this before, but let's look at mean effective pressure. And in chapter 7, when we looked at the Carnot engine, is when we first introduced mean effective pressure. So mean effective pressure, P sub m, is equal to W net divided by the piston displacement, or the work per unit mass divided by the piston displacement on a unit mass basis, which is your specific volume. So V1 is RT1 over P1 is 0.287 times 300 over 100 is equal to 0.861, and V2 is RT2 over P2 or V2 is equal to V1 divided by R. So I have two ways that I could go about finding V2. If I did it the simpler way, I have V2 is equal to 0.1076. And V1 minus V2 is equal to 0.753. And this is V sub PV. So I have that I can calculate and find, we'll find the mean effective pressure.